Thanks for coming. And today I'll be talking about the role of strong consistency in eventually consistent databases. So I'm Duarte, I'm a software engineer at ScyllaDB. I don't do very well at 9 a.m. in the morning, but I'll try to be coherent. And so first of all, what is consensus? What are consensus protocols? So the definition is that they are the process by which a set of unreliable replicas agree on the underlying system state. So these protocols provide strong consistency guarantees about the underlying data. They are usually leveraged to implement what's called replicated state machines, where a set of replicas work together as a coherent unit, and they all reflect each other's state consistently. They are fault tolerant, and a round of the consensus protocol involves a replica proposing a new value for the underlying system state, and the rest of the replicas either deciding on that value or rejecting it. They provide a set of guarantees, so a correct protocol will be stable, where if a replica decides on a value, it will be set in stone, it cannot be changed. All replicas should converge on the same values, they shouldn't decide differently. A correct protocol will mean that a replica will decide on a value that has actually been proposed, so it won't invent one out of thin air. And finally, the protocol around must terminate, so a value must eventually be decided. So before I go on to more details, why do we want to introduce consensus protocols in Scylla, and why do we want to introduce strong consistency? So there are a lot of external use cases that can be enabled by strong consistency. You can have uniqueness constraints. For example, if your application requires a user to have a unique email address, you can leverage this to ensure that. You can implement read, modify, write accesses, where you read some piece of data, you evaluate it, and then you write back a new version without having to worry about concurrent accesses. And you may also want to ensure that your changes are all or nothing. For example, today, if you do a quorum write and it fails, it doesn't mean that the value won't enter the system. So even if one of the replicas acknowledge the write, then eventually through repair and read repair, that value will propagate throughout the system. So if a quorum write fails, it doesn't mean, it just means that at that particular point in time, we weren't able to achieve the desired consistency, and it has implications. It doesn't mean that the value won't appear in the system later. These use cases require coordination between replicas, and they have an inherent performance cost. So we want it to be opt-in, and we want to be making everything strongly consistent in Scylla. The main motivation, however, is that of compatibility with Cassandra, which already has a strong consistent feature called lightweight transactions. Lightweight transactions apply within the context of a partition, so they allow you to have linearizable updates within a partition. They are exposed to the user as a distributed comparent set. There is CQL syntax that allows you to apply a modification only if a set of requirements are met. It is, however, a data path operation, so even though there will be performance costs, we don't want to make it slower than it has to be. And another important aspect is that it requires a read before write, so we are able to validate those restrictions before applying the new update. So how do we go about choosing a consensus protocol with which to implement these things? So the main thing is understandability. This is actually more important than it seems. There's a very famous paper by Google called Paxos Made Live, where they try to implement Paxos, which is like the most famous and well-known consensus protocol. They tried to implement it for Chubby, and then they didn't have a lot of success and wrote a paper about all the challenges that they encountered, mainly related to the fact that the paper is very, very opaque and not very prescriptive. Then we also want to pick an algorithm that's not too new, that is proven by industry and it's very widely used. Another thing to look at is the performance characteristics of the algorithm. Namely, how many round trips, how many messages the replicas have to exchange before they can decide and agree on a value. then how amenable the algorithm is to general performance optimizations that we can exploit. And also, we want to make Scylla not boring again, so we want to choose an algorithm that's hot and fashionable. So another important point is related to those round trips. There's a tension between allowing any node to propose and decide on a value and the number of round trips that are necessary to achieve that. It is typically 2 for protocols like classic PAXes and CAS PAXes. Cassandra has a protocol that requires 4 round trips, mainly having to do with the fact that we need to do that read before write for LWT. What other protocols choose to do is elect a strong leader, and that leader is the only node that can decide on new values. It can do that in a single round trip, but having a single leader limits the throughput, and the request typically has to go through an extra hop to actually go to that leader. So multiplexes, Raft, and Zab, the Zookeeper protocol, are examples of protocols with a strong leader. When implementing a consensus protocol, we have a set of challenges. These protocols typically have an underlying log of operations, which is the way that operations are ordered and actually ensure that the replicas all see the same operations in the same order, and that requires storage and space. Read-only requests usually require a full round of the consensus protocol, where the function we are trying to apply is the identity function. But some consensus protocols have optimizations that make read-only requests much more efficient. Dynamic membership and cluster reconfiguration is an issue as well, so protocols must support that. We would also like to have multi-key transactions, so some protocols can help here. If we want to run the protocol across the wide area network, then we want some decent performance there as well. And finally, and most importantly, we want the protocol to have been formally validated, so we know it is safe. So we chose Raft. It's a very understandable protocol. It's focused on that, actually. The paper and the PhD thesis are very comprehensive, very prescriptive. It is widely used. A lot of open source projects use it. It does have a strong leader, and we'll see how we'll circumvent those limitations. And in the context of lightweight transactions, that leader will be the only one who has to carry out the read before write. And in our case, the required log can be very easily compacted, so we don't have a lot of space requirements. I won't go into a lot of details about the algorithm, just saying that a given replica in a Raft group can be in one of 3 states. It can be a follower, it can be a candidate to become a leader, or it can be the single leader itself. The protocol provides a set of guarantees. In Raft, time is divided into logical terms, and for each term there can be only one leader. The leader never changes the values that have been decided previously, and when we go to elect a new leader, it has to be one of the most up-to-date replicas. Implementing Raft in Scylla won't be a direct translation of the protocol as described in the literature. There are a set of optimizations that we want to make, and there are also characteristics endemic to Scylla that require us to make some modifications. So what we are going to implement is Scylla Raft. So since we don't want to have a single leader for the whole cluster, we take advantage of the fact that the cluster is already divided into token ranges. So what we'll do is we'll have a Raft group per token range. This means that requests for disjoint token ranges can proceed independently. It means that when a leader fails and we have to elect a new one, there will be a period of unavailability. But that will only affect a single token range. The leader won't be such a bottleneck as well, because Scylla is sharded, and within a node, there are many opportunities for a high degree of concurrency. So because a node is responsible for multiple token ranges, it will also participate in multiple Raft groups. And because Scylla is sharded, and in this case it is both a blessing and a curse, each shard will handle a subset of the operations, and this will have implications in how the protocol is adapted. So in a node, we'll have many instances of ref groups, and each shard will have a copy of an instance of a ref group. However, we don't want to shard and replicate everything, namely heartbeats. So in Raft, a leader sends periodic heartbeats to the followers, and that's the way that the followers know that they still have a strong leader. The frequency of these heartbeats is directly related to the period of unavailability where a leader is lost, and a follower must detect that there is no leader and eventually become one itself. Since a node can be a leader for multiple Raft groups, we don't want to send a heartbeat to a replica that is a follower for many of those same groups. So we want to coalesce the heartbeats in a single message. And the reason we don't use gossip for this is that the period of gossip is much longer than we want this period of unavailability to be. The write path is also substantially different from the core Raft algorithm, mainly because of the read before write that has to be done. So when an LWT request goes into the system, we have to acquire some logs, do a read before write, compare the existing value to the restrictions that have been specified, and only if they match, then apply the new write to the log, propagate it out to the followers, and apply it internally. Sharding in Scylla, like I said, is going to be problematic. So first, you might be wondering, since everything in Scylla is sharded, then why do we organize Raft groups per node and not per shard? So inside a node, a token range is divided into many partitions, and each CPU is responsible for a set of those sub-token ranges. And so the reason we don't really want to organize Raft groups with individual shards is because that will lead to an explosion of state. That will mean we'll have a lot of groups, and all the metadata we have to keep will make this unattainable. Another issue is heterogeneous clusters, where different nodes have different shard counts. So in the typical case of a homogeneous cluster, one leader shard will talk to one follower shard, and that follower shard will contain an exact copy of the state of the leader. However, it can be the case that we have heterogeneous nodes, and now two leader shards are sending commands to the same follower shard. And this has a lot of consequences in the way we organize internally the algorithm, because if that follower shard ever wants to become leader, it has to make sense and order the messages that it had been receiving from those other two shards. So this will make Scylla Raft a bit different from plain Raft as implemented in other projects. Another issue is resharding, where we can reboot the node with a different shard count, so we have to readjust the internal data structures as well. So what I've been talking about so far applies within a single partition. So, however, we don't want to limit ourselves to this. We want to have multiple partition transactions, even though Raft groups are only responsible for a particular subset of the token range. Related to this is another important LWT constraint. So in LWT, you can specify a consistency level called local serial, which means that a lightweight transaction operation should apply only within a single data center. This is for performance reasons, so we don't incur in wide area network traffic. This means, in our case, that a Raft group cannot span multiple data centers. So we must have a Raft group per partition range per data center. So we are left with the converse problem. Now, if the user wants to use the serial consistency level and wants an LWT operation to apply across data centers, we must somehow coordinate between Raft groups for the same token range. And the way we're going to do that is by layering yet another protocol on top of Raft groups. This represents more upfront work for LWT, but it will pay dividends later because it enables us to support multi-partition transactions. And the way this is typically done is by layering on top of two ref groups or more an agreement protocol, such as two-phase commit, which in this case works nice because if two leaders are running an instance of an agreement protocol, because the leaders are in a ref group and have a fault tolerance, if one of them dies, then a new leader can be elected, and the transaction, the agreement protocol, can continue where it left off. So I've talked about external use cases. So LWT will enable all of the strong consistency external use cases. But inside the database itself, we have many features that can benefit from these mechanisms as well. The first one is concurrent schema changes. So today, if you make a schema change, then it is carried out locally at a particular node and then spread throughout the cluster eventually. This means that there is no protection against concurrent schema changes. So if you do things like creating a table with the same name and even with the same schema, that will lead to conflicts later on. So one way to solve that is by, in this example, we're trying to create a table using a particular user type, while at the same time trying to drop that user type. These operations will not be ordered and will lead to conflicts later on. One way to solve this is to have a distributed system table, where the key can be, for example, the key space. And we will then have a ref group that's responsible for a partition range and thus for all the operations affecting a particular key space. And that ref group will represent a central point through which these operations will flow. And it can then order them and make sure there won't be any errors down the road. Another issue is range movements. So today, concurrent node movements, concurrent range operations are discouraged. You typically have to add one node at a time because overlapping ranges can be selected, and you end up wasting a lot of work. Related to this, that token selection is not optimal, it's kind of random. And again, having some strong consistency mechanism, some central point, can allow us to solve these problems. We can even take it a little bit further and think about Scylla balancing itself as time goes on, since we can have this central component making global decisions about the cluster. And since these are global decisions, since we can't take a partitioning approach like we did before, where we were partitioning things by key space. So we'll have to either have a global group where all of the nodes are part of a ref group and there is a single leader to serialize all these changes. There are some issues with this. So we can think about having a specific group. For example, all the seed nodes are in a ref group, or the first n nodes of the token ring are in the same group. And then they do provide us this central point that can make cluster-wide decisions. A final example is materialized views. So today, when updating a view happens asynchronously, this has advantages, namely that base table availability is not impacted. So if I do a write to a base table, I'll store the view update in a queue. So even though the view may not be available at a particular point in time, it will be available later, and the update will go there later. That has a set of drawbacks too, namely that those queues might fill up. We might have to shed load and drop those view updates. It also means that the user has no guarantee and no idea about how and the view will be updated. So again, strong consistency can help us, namely multi-partition transactions. So we can imagine that a view is updated in the context of the same transaction that is updating the base table. And this is it. But before we go, I just want to say that this is all still in the design stage. We have nothing concrete yet, but this is the direction that we want to go into.